Real-world robots frequently face uncertainties from internal model mismatches and external disturbances. Accurately perceiving these unknowns remains the primary challenge for high-performance operations. Beihang University's research team published in the top journal IJRR a FORESEER framework satisfying +2 disturbance learning algorithms, SEER1 and SEER2, address robot performance degradation due to internal model uncertainties and external disturbances. 5 drone configurations performed 4 indoor or outdoor missions under uncertainties in mass, aerodynamic drag, rope tension, and rainfall. NOKOV Motion Capture System provided high-precision drone pose data in indoor experiments, validating the framework's effectiveness. In indoor experiments addressing mass uncertainty tasks, a drone equipped with a robotic gripper grasped objects of unknown mass and released them mid-flight, inducing abrupt mass changes. The results demonstrate that the SEER1 algorithm accurately estimates mass uncertainties. Comparative evaluation of FOR controllers in vertical plane tests demonstrated that SEER1 accurately predicts mass uncertainty while remaining robust to other uncertainties. Experimental results show its ability for uncertainty separation. The SEER1 is generalized to a small drone without any change. Different levels of payloads are considered. Experimental results show its robustness. Outdoor tests also show its robustness under lower precision state estimation. A foam board is attached to the drone to increase the drag. Tests at different speeds show the effectiveness of the SEER2 in comparison with other 5 methods. A drone with self-perception ability is commended to fly through a crowded place within a wind field. The algorithm estimates external wind disturbances to enable energy and time-efficient pre-flight trajectory planning. Outdoor results show its robustness under lower precision state estimation. The experimental setup is shown here. The effectiveness of SEER2 was validated through outdoor flight tests under rainfall. The flying drone is commanded to drag a car with an inelastic rope. The rope is sometimes loose and sometimes tight. A test with 1.7x faster flight speed is implemented. Both slow and fast tests show that SEER2 accurately captures rapid uncertainty variations, resulting in superior tracking performance after feed-forward compensation, which validates its effectiveness against step-like uncertainties. The trajectory is set as a circle, in which the tension is more stable. The NOKOV Motion Capture System provided high-precision drone pose data for indoor trajectory tracking and performance evaluation. Extensive tests reveal the sufficient prediction accuracy of the FORESEER on various uncertainties, from internal model uncertainties to external fast-varying disturbances, without any additional sensors.